y prime equals to limit as h approach 0 y of x plus h minus yx divided by h. Now for small h, when this h is small, also h must be greater than 0, but is small, the following equation can be written as I'm ignoring h here, I'm just taking out the limit. Now rearranging this equation, I have yx plus h equals to hy prime x plus yx. Okay, now if you recall, this y prime here is also my function of f. So y plus h, we have yx, and the rearranging the equation, plus h f of x y. So this is the idea of this Euler method. Now numerically we can replace the exact method with the approximate value. So this yx plus h I can write as yn equals to yn minus 1 plus h f of xn minus 1 yn minus 1. Okay, so we have the Euler method. Write this as number 2. Maybe I'll write it to number 1. Okay, so we have number 1 here. It's the Euler method. Now let's look at something such as local error. Okay, local error. So normally we know what is the local error. Local error. So local error, where your approximation approximation minus the exact solution. So this is the definition of error. Local error for this case is denoted by, let's say, ln unxn minus yn. Now unxn is actually the exact solution. Okay, this is actually the exact solution. Exact solution at each step, and this is the Euler method. Okay, so now what happened here, if we can see that, so local error is actually my error committed at each step. These are called the local error. Okay, now for the global error, the global errors, the errors we know is exact minus approximation, approximation minus exact. So it's denoted by en, which is my exact solution minus with my approximate solution. Okay, so this is the error after n step. Okay, the error at n step. So you can see that this is my y of x and minus, now y hand here, if I write this equation here number 2, if I write yn equals to ln minus un. So I have un xn plus yn. Okay, so we have equation number 3 for the global error. Now what is the error in Euler method? Now error in the Euler method, okay, we know that this method, if you want to take the Taylor series expansion, we have y1 equals to y at x naught plus h f of x naught y naught. Okay, or normally you write as yn. Okay, normally we write at 1. This is for one step. So this is for one step. Write it properly. This is for one step. Okay, when you take the Taylor series expansion of this one will be y x naught plus h plus h2 over 2 factorial y double prime x naught higher order term. Okay, now x naught plus h is my y at x1. Okay, and then we have whatever term involving h2 over 2 factorial y double prime x naught. Okay, so if we use the same concept, we want to see the error of the Euler method. So what is the error? So we can see that for one step method, we have y1 minus y of x1 equals to so what this means? This means that the local truncation error, this is my local error, is proportional to h squared. Okay, similar to that, we can also say the order of the numerical method, particularly the Euler method. Okay, we can show that provided for fx is sufficiently differentiable, we have E equals to CHP plus 4 to the power of HP plus 1. Okay, so E is the global error. So this is the global error, and C is just a constant, and P is a positive integer. Okay, so from here we can say that where P is also the order of the method. So if you look at the local truncation error here, where you get the Euler method is proportional to h squared, so that we can say that the order is of 1. Okay, because of we have this term here. Okay, that's it for the error of the Euler method. Now we would like to see another one called the convergence. The convergence of Euler. Okay, so we know that the local error, the local error, Ln, is given by, earlier on our equation 2 will be given by un xn minus yn. Now, this unxn, the error at xn, okay, the error at xn, I can say that usually y at xn minus 1 plus h minus with, this is my Euler method. So we have y xn minus 1 minus h f of xn minus 1 y at xn minus 1. Okay, these are the Euler. Okay, I hope you understand this term here, why this is become like this. So consider my term, this is my interval, this is xn minus 1, y at n minus 1. So this is my xn. So to reach xn, okay, so xn equals to xn minus 1 plus h. Okay, so this is the idea. Okay, so by the Taylor series expansion, expanding this in terms of series, so we have y at xn minus 1 plus h y prime xn minus 1 plus h2 over 2 factorial y double prime xn minus 1 plus theta h minus with this whole term y at xn minus 1 minus h. I can write f as y prime xn minus 1. Okay, this f is written as y prime x. Now, taking out the term, this term cancels out, this term cancels out, this leaves us with h2 over 2 factorial y double prime xn minus 1 plus theta h. Now, we want to make sure the theta is from 0 to 1. Okay, if the second derivative is bounded by some constant k which is greater than 0 on this interval, okay, then we can say that this y derivative x is less than equals than k for all x in this interval. Okay, therefore our local error is also bound by half x squared k for all n. Okay, so this is the convergence for the local error. So we will look at the convergence for the global error in our next slide. Okay, that's all. Thank you.